All right, so welcome to Math 331. This is lecture 2. And so what I want to do today is I want to talk about proofs by induction. So everybody has said that they are comfortable and they're familiar and they've seen proofs by induction. So I will assume you are either telling me the truth that you're comfortable with this, or you can very quickly get to the point where you will be comfortable with this. This is a skill you learn how to do in graduate school. Oh, yeah, I know that very, very well. All right, tonight, meet up with friends and learn X. Okay, and if you do want to hear more details, just let me know. There's going to be a lot of stuff in the slides that I'm not going to cover in class, just putting in a few more explicit examples, just going through all the details of how do you prove some of these things by induction, just so if you want, they're there, you can look at it. The way I view a lot of mathematics, as I mentioned before, is baby is crying and you're trying to figure out why baby is crying, and you go through your list. In the beginning of the semester, when you don't have a very long list, it's not too hard to figure out what to try. As the semester gets longer and longer and longer, and we hear more techniques, it becomes more interesting. And the goal is to try to look at a problem and get a feel for what's a good order to try things. This is where AI is going to become a game changer, because AI is not going to bother trying to find a good order. It's just going to try everything. And that makes a huge difference. All right, so just to finish up from yesterday, and again, yesterday always means last lecture, tomorrow always means next lecture, unless I specify otherwise. This is the Mathematica code that I wrote years ago to find which way to put in the numbers so that they add up to 1. And Angus was very kind to send his comments on how to do the code in Python. You did have things in very nice color, which I have dropped because when I pasted it, some of the grays were no longer visible. And rather than going through and changing everything, it was just easier to just paste everything in one color black. Okay, just to get a little bit of a familiarity with people's backgrounds, if you've done algebra like this earlier with me, don't speak up, but I just want to make sure everybody can do basic algebra. 16 over 64 in lowest terms? 1/4. Okay, excellent. So this is looking good. It's one of the difficulties when you teach early in the morning is people are sometimes still asleep. If you want to bring coffee, you're welcome to do so. If you want to bring coffee for other people as well, that's also fine. If you want to bring food, not a problem. If you want to bring a pillow, that's pushing it a little bit, we'll talk. All right, 49 over 98. 1/2, excellent. 19 over 95. 1/5, great. And let's just do one more. 12 over 24. Yes, it is 1/4. Because 16 over 64, you cancel the 6s and you get 1/4. The 19 over, so the 49 over 98, you cancel the 9s and you get 4/8, which reduces to 1/2. 19 over 95, you cancel the 9s. So clearly the way you divide two-digit numbers, if they have the same on the anti-main diagonal, is to just cancel. And I've given you 3 data points. And what I could have done is I could have just given you the first two and then claimed 12 over 24 is 1/4. And then if you dispute me, I said, well, let's just choose another one at random. Let's choose, 19 over 95 and keep something in reserve. There's other examples like this. I strongly encourage you to look up Euler's prime producing polynomial. So this is a function, a nice quadratic polynomial where like the first 40 plus values are all prime. And then eventually it stops producing primes for a while. So you've got to be very careful. Just because you check something for a little bit does not mean it's going to continue. You start to get more and more confident, but you also have to be a little bit careful as to who is giving you the data, and are they giving you the data in a very specific way? Are they trying to mislead you? So we have a rigorous procedure to prove things by induction. And so again, I'm not going to go through all of these slides because people know they're there, but this way, by at least showing them briefly like this, you can hit pause on the screen, and you can also, of course, download. So to prove things by induction, we basically do a ladder approach. We have some statement P of n. Maybe it's the sum of the first n integers is n times n plus 1 over 2. And we show that P1 is true, and then we show whenever Pn is true, Pn plus 1 is true. And then this allows us to claim that Pn is true for all n. Sometimes we start off with n equals 0 rather than n equals 1, depending on what problem you're looking at. Sometimes you might start off with n equals 2. But it's from that point onward. And so there's an initial case you prove, and then we just go through, well, if Pn being true implies Pn plus 1 is true, and we know P1 is true, take n equals 1. We know P1 is true, P1 implies P2, P2 is true. Now we take n equals 2. We know P2 is true, P2 implies P3, P3 is true. Okay. So I'm not going to go through, bless you, the various stuff. This is just this way they cannot be there. Sometimes we like to do not just brute force P1 is true, but we sometimes check just a few cases just to build up some ideas of how to attack problems like this. And the idea is it's basically a ladder. We have P1, P1 implies P2, now we have P2. We have P2, P2 implies P3, now we have P3. We just walk up like that. I'm not going to go through and do this, but this is the standard problem you should have seen, that the sum of the first n integers is n plus 1 over 2. Anybody know what these numbers are called? I'm sorry? Nope. 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 These are the triangle numbers, right? So this is basically giving you an explicit formula for the sum of the triangle numbers. And you can do other shapes as well, and they have names, and they have formulas for them as well. Anybody have any idea why we might care about this? Every now and then I do like to ask the who gives a damn question, right? Why would we care? Good. So one thing is, if you actually have sums like this, which can arise in a lot of problems, rather than adding all of the stuff, we can just jump to the answer. So if we have an explicit formula, great. And you might see stuff like this coming up in maybe averaging various things. How many of you have seen the fundamental theme of calculus? This is basically, are you awake right now? There's no way you can be this deep in a math major without having seen the fundamental theme of calculus, unless you have a math teacher who deserves to be prosecuted for criminal negligence in teaching you calculus. Why do we care about the fundamental theme of calculus? Why do we care about areas under curves? But why? Why do we want to calculate areas under curves? I agree it's more efficient, but why do we care about areas under curves? Okay, so you might be able to relate this to certain problems. I have a certain area, and I'm going to need to calculate what is this area so that I know how much supplies to buy. So that is a legitimate reason as to why you might care. Another reason you might care is frequently areas under curves represent probabilities. And so if we want to calculate the probability that something happens, we can often convert this to a calculus problem. And sometimes we can even get nice closed form expressions. If you want to prove the fundamental theme of calculus, that's a wonderful exercise. But you can at least verify, is it reasonable? Is the area under the curve, is that limit of the Riemann sum going to equal the antiderivative at b minus the antiderivative at a? Well, what's the simplest function I can look at? I could look at f of x equals 0. It's a little bit too simple. I could look at f of x as a constant, in which case the area under the curve is just a rectangle. It's not that hard to show that the fundamental theme of calculus works for a rectangle, but it's also not that impressive. The next simplest I could look at is f of x equals x. That's this function. This is what would happen if you did the Riemann sum. And so as a nice exercise, try to do the Riemann sum using this and verifying the fundamental theme of calculus. If people are interested, I'm happy to go into more detail on this either later today or tomorrow, just throwing some things out there. However, at the end of the day, you verified the area under the curve of a straight line. You've basically calculated the area of a triangle. This is not cause for celebration when you're trying to explain to people why we care about the fundamental theme of calculus. You found the area of a triangle. I already knew how to do that. Do you know how to find the area under a parabola? And instead of looking at the sum of the integers, if we look at the sum of the integers squared, that's the Riemann sum that will emerge. And now all of a sudden, we have a non-trivial verification of the fundamental theme of calculus. So here's one reason why we might actually care about executing these sums. It provides a way to check and make sure that when we're doing calculus, we're doing it correctly. All right. So I am not going to go through, and I'm not going to show why all of this works, but I will pause the slides for like a brief second, because people can always then just hit pause if they really care, and just going through all the details the algebra is pretty straightforward, which is nice. Okay, more straightforward algebra. Okay, and then you're just doing formulas for sums of squares now. It's very similar. No surprises. How many people have done sums of squares already? Have you done this before? There are formulas for higher and higher ones. It's a really interesting challenge to try to come up with closed form expressions. And so if I tell you what the formula is, it's not so bad to do the proof by induction. But if I don't tell you what the formula is, now all of a sudden you have to figure out what is it. One way you can do that is try to do small cases by brute force. I'm not going to do the sum of the odd numbers. It's a nice way to prove that you by induction that the sum of the first n odd numbers is n squared. You can give a nice geometric proof as well as to why this is true. Okay. Here's another induction proof. Prove that 133 divides 11 to the n plus 1 plus 12 to the 2n minus 1. And so when you see 133, what's the first thing that comes to your mind when you see 133? 12 times 11. So, well, if I want to show that it divides, 12 to the 2n minus 1, the 12 part is clearly going to divide that, but maybe I have an issue with the 11 part. And same things for the other. So I want to maybe somehow write the 11 in terms of 12 or the 12 in terms of 11. And I've got some extra factors. So you might want to play some games with factorization and whatnot. So I will not show the details for this, even though I will leave the details in the slides. But this is a slightly different proof by induction. You could, of course, try to just do it directly. Can I somehow pull things out? Or if I know that it divides it for n, can I now somehow show that it divides for n plus 1? And how do I try to rewrite things? All right, so let me skip a little bit ahead. And so before going and doing some more interesting proofs by induction, rather than proving a result, I want to try to get a question to you, is this result reasonable? So in this class, you are encouraged to be a smartass. Okay, you are encouraged to cover your ass and answer questions in such a way that you know you will be correct. Then you can try to be clever and get the best answer possible. I want upper and lower bounds for the sum of the first n integers. Can somebody give me either an upper or a lower bound that they are willing to bet their life on? Because I've got in trouble when people bet the lives of their friends. So it's going to be your life. You are guaranteed that you are correct with this upper bound or this lower bound.
N to the power of n for the upper bound.
Good. So we know 1 plus ... plus n is less than or equal to n to the n. That's the second worst upper bound I've received. There's one worse upper bound I've received. You want to try what the worst upper bound is? Yeah, infinity. I have had students say it's less than infinity. That is clearly safe. We have n terms. Each term is at most n. So this is at most n to the n. N to the n seems a bit excessive, but sure. Can you do a little bit better than n to the n? I think n to the n is a bit excessive, but what's something a little bit better than n to the n? N squared. So this is also going to be less than or equal to n squared. Because we know we have n terms and each term is at most n. Can you give me a lower bound? 0. No one actually gives me negative numbers as a lower bound. But can you give me a better lower bound than 0? You can give me 1. N. And so now we see that it's somewhere between n and n squared. So this is not good enough to have a sense of what the true order of magnitude is. What we can do is we can say the following. All we have to do is either improve the lower bound to be of size n squared, and then we'll have the order of magnitude, or improve the upper bound to be of size n, and we'll have the correct order of magnitude. Or if both of them are wrong, somehow do a meet in the middle. So which do you think is the right order of magnitude, n or n squared? So what do you think the right order of magnitude is for the sum? right? Yeah. We have the claim from induction that it's n squared over 2 plus n over 2, or n times n plus 1 over 2. So from our analysis by induction, we expect that this is going to be quadratic in n. So I expect that the n squared is closer to the truth than the n. So can somebody give me a better lower bound? So the problem is, to get the lower bound of n, we replaced everything with 1. Rather than replacing everything with 1, let's replace some of the things with something smaller. Any thoughts? And I understand that n may not be an even number, and this could be a slight abuse of notation. What can you give me for a lower bound here? So how many terms do we have? N over 2 terms. And how large is each term? At least. So this is going to be greater than or equal to n over 2 times n over 2, which is n squared over 4. So we know that the sum is at least n squared over 4. It's at most n squared. It's somewhere in between. And this gives us the order of magnitude very easily. This is called, let's call it maybe like a divide and conquer, where we're breaking it up into 2, like a dyadic decomposition. And you could keep iterating this. We could then break each one of those again in half and get upper and lower bounds and do stuff like this. You can do this for the factorial function to try to get a sense of how large is n factorial. You could play games like this. And if people are interested, I'm happy to talk about how can you play games like this and get a sense for the size of an object. Because for a lot of things, I really care about how is it growing with n. I don't really care about is the constant 1/4 or 1/2 or 1. I care about what is the dependence on n. And this very cheaply gives me the dependence. Okay. So the hardest thing when you're trying to prove these things by induction is to know what the formula is. If I tell you the formula, it's a very mechanical procedure to go through. If people are interested, we can talk a little bit later about how do you try to find what these formulas are. And I actually have a paper, it's extremely painful, but no thinking is required, just algebra, and it will give you the answer. But the algebra quickly becomes so unpleasant, you do not want to do it, but it will work. So I want to do a false proof by induction. I want to prove that everybody has the same name. It's great if I can get a volunteer who's willing to have their name divulged. Is there anybody here who's willing to have their name divulged? Do you have identification on you? Okay. Okay. We're going to prove everybody is named Ahmed. You keep that out just in case anybody objects. Okay. It's readily accessible.
What's that?
It's readily accessible.
Yeah.
Okay. Does everybody believe that they're named Ahmed? Why not? All right, so would you like me to prove by induction everybody is named the same?
Yeah.
Okay, so my statement Pn is going to be in any group of n people, everyone has the same name. That doesn't mean if I have 2 different groups of size n, the 2 different groups could have different names. Just whenever you have a group of n people, everybody in that group has the same name. That's my inductive statement Pn. Let's start with the base case that in any group with 1 person, everyone has the same name. And the inductive step will be if everyone in a group of size n has the same name, we get to assume that, and then we need to show that in a group of n plus 1, everyone has the same name. The base case, does anybody dispute the veracity of the base case? Why? Why is the base case reasonable? Good. If the group only has 1 person, everybody in the group has the same name. So the proof is immediate in that case because there's only one person in the group. So clearly everyone in the group has the same name. So let's consider Pn is true and we want to show Pn plus 1 is true. So I downloaded some wonderful images from the web. And so here are my n plus 1 people. Can someone give me a group of n people inside this n plus 1 set? So can somebody give me a set of n people? Well, no. I'm listing n plus 1 people here. Choose n people from this n plus 1. Can somebody give me a nice procedure to choose n people? So, okay, so choose the first n people. So if we choose the first n people, they all have the same name by the inductive hypothesis. Can someone give me another set of n people? The next one. They all have the same name by the inductive hypothesis. So the first n all have the same name, the last n all have the same name, but peoples 2, 3, 4, all the way up to n are in both groups. So everybody in the first set has the same name as person 2. Everybody in the last set has the same name as person 2. Therefore, everybody has the same name. What's wrong with this? I'm sorry, please raise your hand if you want to speak. Yes, Amin.
Showing that the A plus 1 person is the same name as the other set of 1, 3.
I have, because by the inductive assumption, I'm assuming it's true whenever I have a group of n people, and then I have to show it's true when I have n plus 1 people. By the inductive assumption, the first n people all have the same name. By the inductive assumption, the last n people all have the same name. So everybody in the first set of n people has the same name as person 2. Everybody in the last set of n people has the same name as person 2. Therefore, everybody has the same name as person 2.
P1 does not imply P. It's very, very small.
So what's really going on here is imagine n equals 1. Then n plus 1 equals 2, and there's no overlap. There's a break in the staircase. If we knew that in any group of 2 people, everyone has the same name, then it would hold in general. Then you would have an overlap. When I drew the picture in a very misleading way. I made you think that there were a lot of people because the small cases we should be able to just handle directly. No, sometimes the small cases are the ones that cause trouble. So you have to be very careful when you're writing things down that you don't put in any additional information that's not supposed to be there. I am pretty sure I hit record at the start. I'm going to just double check and make sure it is recording. Yes, it is recording. Excellent. Okay. So this is one of my favorite proofs that can go wrong. You can use this idea to prove a lot of interesting results. You can prove every positive integer is a perfect square by making a very similar mistake like this. So as a nice exercise, give a false proof, I'll make this extra credit, that every positive integer is a perfect square by making a similar mistake like this. Okay? All right. So what I want to do now is I want to turn to the product rule and induction. So this is something you should have seen before from calculus. So I will assume everybody is masters of basic calculus. The way you prove the product rule typically is if we say, a of x is f of x, g of x, a prime of x is the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x over h. And whenever anybody writes something with a huge space like this, obviously there's a reason. So does anybody remember how you prove the product rule? How do we prove the product rule? Who remembers the product rule?
Well,
derivative of product of
Ye-
functions.
yes.
It's a function times the derivative of the second plus derivative of the first times function. The second
Yes.
function.
You're correct. Normally we do it the other way. Normally we say f prime g plus fg prime.
Okay.
You're completely right, but normally we do it that way. And it makes things a little bit nicer in terms of where the minus sign is for the quotient rule. So the way this is typically done is we add 0. So there are two ways to do nothing in mathematics. One is to add 0. How else can you do nothing? Multiply by 1. And I learned this from Peter Jones, one of my professors at Yale, who said, actually, the log of 1 is 0. So there's really only one way to do nothing in mathematics. It's really good to learn how to do nothing so that you can take an expression and rewrite it in a more conducive manner. I'm going to write this as minus f of x, g of x plus h, plus f of x, g of x plus h. And when I write it like this, doing some simple limit rules, this is the same as the limit as h goes to 0, f of x plus h minus f of x over h times g of x, plus the limit as h goes to 0 of f of x, g of x plus h minus g of x over h. I'm using the limit of a sum as the sum of the limits. This is okay so long as at least one of the limits is well behaved. And then this just becomes f prime of x, g of x, plus f of x, g prime of x. Okay. It seems like some people had a little trouble remembering or recalling how to prove the product rule, which is fine. It's been a while since you've done calculus. And this is also the 21st century where this is all done by computers now. If you were the supreme being, is this how you would define the product rule for two functions? What might you choose the product rule to be?
Derivative of the product.
Yeah. Well, okay, you gotta say it correctly. The derivative of the product should be the
Derivative times derivative.
good, the product of the derivatives.
Yeah.
And the derivative of a quotient should be the quotient of the derivatives, right? And as a nice exercise, you could ask, for what pairs of functions will this be true? So one of the things is to try to sniff out what is the product rule. If you know what you're trying to prove, it's a lot easier. So can you build some intuition? One of the key things is to try to get a sense of functions whose derivatives we know. We know the derivative of x to the n is n x to the n minus 1 if n is a positive integer. What result is used to prove that? I'm sorry? Binomial theorem. So this follows from the binomial theorem. X plus y to the n is the sum n choose k, x to the n minus k, y to the k goes from 0 to n, and then we'll just take y equals h. So hopefully you've seen the binomial theorem before. All we really need is that x plus y, h to the n is x to the n plus n x to the n minus 1 h plus terms of h squared and higher. That's all we really need, because then when we subtract off x to the n, the x to the n's cancel. When we divide by h, we get n x to the n minus 1, and then the rest of it is still going to have an h. So when h goes to 0, it's not going to matter. So there's a lot of ways to prove the binomial theorem. So one thing is, prove the binomial theorem. And there's, again, lots of ways to do this. A lot of it comes down to how do you define n choose k? And so hopefully you've seen that n choose k is n factorial over k factorial n minus k factorial. It's the number of ways to choose k objects from n objects when order doesn't matter. A lot of what I want to do in the first few classes is just throw some materials and topics out so that if you want to see things in greater detail later, I have some idea of what you're interested in. One way you could try to prove this is x plus y to the n plus 1 is x plus y times x plus y to the n is x times x plus y to the n plus y x plus y to the n. And you can now see, hopefully, the n plus 1 choose k plus 1 is, if I'm doing this right, is n choose k plus n choose k plus 1. But this is, the Pascal's triangle. There's a reason why we have formulas like this. And we'll talk more about this when we get to proofs by story. So we'll see more about why this is true. Does this look vaguely familiar to some of you in terms of how this is proved? Okay, so we can talk much more about this when we get to proofs by story, and there's a lot of wonderful properties, hidden. I want to talk a little bit about gathering data. So this is extremely important. And if anybody is interested in, writing a math outreach article, I think this would be a wonderful topic for math outreach article. How do you sniff out the product rule? We need to find some functions whose derivatives we know. Can somebody give me a simple function whose derivative we know? Is x. Or more generally, not just x, we could do, so we could do c times x, or we could do x to the n. So what we could do is we could take f of x is x to the n, g of x is x to the m, and then a of x is f of x, g of x is x to the n plus m. F prime of x is n x to the n minus 1. G prime of x is m x to the m minus 1. A prime of x is n plus m x to the n plus m minus 1. And then a prime of x should be a function of f, f prime, g, and g prime. If f equals 1 or g equals 1, we know what it reduces to. So know if f of x or g of x equals 1. Should it be symmetric in f and g when you look at the derivative of the product? It should be symmetric. So again, before I do any calculation, I already have some feel for the answer. It's got to be symmetric in f and g. If f equals 1 or g equals 1, it's got to reduce to what I already know. I've got to somehow get to terms of size x to the n plus m minus 1. When you look at this, there seems to be a very natural way to get terms of size n plus m minus 1. What are those ways? Well, how can I get a term of size x to the n plus m minus 1? You look at f, f prime, g, g prime. How can I combine things? Yeah, cross multiply. If I look at these, if I combine those, and if I combine those, I would get m, let's do it the other way. We'll get n x to the n minus 1 x to the m plus m x to the n x to the m minus 1. And then that's just going to be n plus m x to the n plus m minus 1. This is not a proof, but it's strong evidence. As another example, you could do f of x equals sine of x, g of x equals cosine of x, and then a of x is sine x cosine x. Does anybody know the derivative of sine x cosine x? Well, I can't use the product rule because the whole point is to try to come up with another test of the product rule. How could I rewrite sine x cosine x? Half of sine 2x. So this is 1/2 sine of 2x. So that becomes another way to test to see if the product rule is correct. Again, this won't be a proof of the product rule, but it's going to give us some strong support that the derivative of a product is f prime g plus fg prime. Most of you are not going to be in a situation where you will have to prove the product rule in the future. Most of you might not even ever use the product rule in what you do in life. But this idea of how do you gather data, how do you formulate a conjecture, how do you test it, how do you look at special cases, that's what I want you to get out of this class. That's the perspective that's going to be valuable, not the specific content. We can, of course, prove some of these things by induction. So claim the derivative of x to the n is n x to the n minus 1. So let's assume we know the product rule. Assume we know the product rule. That's terribly written word rules. Let's try to write it a little bit better. So base case, did we just lose the video? Okay. So the base case, when n equals 1, that's straightforward. Yes? Okay, so we agree that it is straightforward when the base case. So now let's do the inductive step. So we can assume the derivative of x to the n is n x to the n minus 1. So now let's consider the derivative of x to the n plus 1. How should I write x to the n plus 1?
X times x to the n.
Yes. There is one other way you could have done it. What's the other way you could have done it? It's almost the same. You're doing x times x to the n. There's one other way you could have done it. What's the other way? X to the n times x, right? Doesn't matter which way you do it. I think it's a little bit more natural to write it as x times x to the n, but either way works. And now, this is going to be the derivative of x times x to the n plus x times the derivative of x to the n by the product rule. And then this is going to be 1 times x to the n plus x times n x to the n minus 1 by induction. And then this is just going to become n plus 1 x to the n. So if you've not seen this before, here's a way to calculate the derivative of x to the n without using the binomial theorem. We have bypassed the binomial theorem. So it's sometimes a nice exercise to get a sense of how deep is a result. How much do we really need to know? What do we need to know to prove the product rule? We're not using the binomial theorem there. Right? Notice that this is only working when n is a positive integer. But we've bypassed the binomial theorem. We've now proven the derivative of x to the n is n x to the n minus 1 whenever n is a positive integer. That's not bad. Okay. So what I want to do now is I want to talk a little bit about Fibonacci's. So I am actually happy to announce I am the president of the Fibonacci Association. There really is such an association. So if you have any Fibonacci needs, please let me know. We unfortunately just had our big conference, so the next one is not going to be for 2 years in Istanbul. But if you are interested, let me know. there's a lot of different ways of defining the Fibonacci numbers. And depending on what you're doing, some definitions are a little bit better than others. We will go with the definition of f0 is 0, f1 is 1, and fn plus 1 is fn plus fn minus 1. So our sequence is 0, 1, 1, 2, 3, 5, 8, dot, 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 dot. Has everyone seen the Fibonaccis before? There's a lot of fascinating problems and properties of the sequence. Years ago, the record was asking math and stat professors for what is your favorite constant and why. And I talked about the golden mean, which is 1 plus root 5 over 2. And I said it has a lot of remarkable properties. One of the most remarkable properties about it is that if you take the reciprocal of the golden mean and then take its inverse, you get back the golden mean. And so I said that with a straight face, and the record printed it. It's a remarkable property. It's equal to the inverse of its own reciprocal. It's amazing. There is an explicit formula for the Fibonacci numbers. This is one of my favorite formulas in all of mathematics. This is Binet's formula. The nth Fibonacci number is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. When you look at this, it does not seem like this should be correct. What kind of numbers are the Fibonacci's? Counting numbers. This involves square roots, it involves divisions. Miraculously, everything cancels. And going back to a comment from earlier, this formula allows us to just jump to any Fibonacci number. In principle, is it difficult to calculate the millionth Fibonacci number? In principle, is it difficult? No, it's just a bunch of addition. If I told you I will give you A pluses in every course you take at Williams, if you can by hand calculate the millionth Fibonacci number from scratch by adding before you graduate, would you take the deal? So you want to get a sense of how quickly do the Fibonacci numbers grow, how many digits, how many calculations, how many can you do by hand? So can you try to estimate how many calculations would you have to do to get up to 1 million? And you will see that it is not a good deal to take. And then the question is just how high of an n do you think is reasonable to get in 4 years? If you want, you can assume without loss of generality that the entire campus is devoted to your well-being and everybody is happy to help. Right? Do we have enough people on campus to get up to 1 million? Now, I said that there's a lot of ways of defining the Fibonacci's. One way to define the Fibonacci's is through tiling. And so we have a block that's 1 by 2, and we can have it either way, like this. And I'm going to give you a long, Hershey candy bar. And I keep a bunch of these actually in my office in case it's ever needed. And the question is, how many ways can you cover a 2 by n with 1 by 2 and 2 by 1 tiles? So how many different ways can I do this? Well, we can start off by doing some small values of n. If n equals 1, how many ways are there to do it? One way. If n equals 2, how many ways? 2 ways. If n equals 3, then the question is, how many ways are there to do it now? 3. And so you can see that there's 3 by, I could do the first one vertically like this, and then do the next 2 like this. Right? How else could I do it?
Flipping it horizontal.
I'm sorry?
And symmetrically.
Well, let's try to do it in order. So I first put one vertically. And then once I did that, I said I could do the next two horizontal. Is there anything else I could have done?
All of the vertical.
If I start off with the first one vertical, what else could I do?
Same order.
I could do the next one vertical and the next one vertical. And that's all the ways to do it with the first one is vertical. If the first one is not vertical, then I have no choice. The next one has to also be horizontal, and this is then forced. What I hope you see is that things naturally split into two groups. And if you look at it, if the first one is vertical, it's now we've reduced the problem to a smaller size. So if first vertical reduces to a 3 minus 1 or a 1 by 3 minus 1. If the first is horizontal, second must be horizontal, reduces to a, oh, sorry, this should be a 2 by 3 by 1. To a 2 by 3 minus 2. And what's really going on here is to tile a 2 by n with 1 by 2 and 2 by 1 tiles. If we let an equal the number of ways, we get an plus 1 is an plus an minus 1, with a0 equals 0, a1 equals 1. So what do these have to be? Fibonacci's. So this is one of the most standard problems. This is a nice induction. And we have a really wonderful answer. I believe I am the master at multitasking in terms of trying to get credit for the same thing from many different places all at the same time. This is the only way I can do all the stuff that I do. So I need to combine teaching with research, with playing with my kids, trying to do everything all at the same time. This is one of the reasons why I teach a class like the mathematics of Lec02. It's one of the greatest ways to do everything all at once. Whenever you see something in mathematics, you should always ask, how can I push this forward? How can I extend this? What would come next? There's a bunch of natural questions you can ask, so it looks like you're paying attention even if you're not. What if I remove this condition? What if I increase the dimension? And so what if we increase the dimension here? What if we have instead a 2 by 2 by n and 1 by 1 by 2 tiles? And again, when I say it like this, you could also have a 1 by 2 by 1, however you need to orient them. You can always play with them. How many ways are there to do it now? So now, I have something like this going down like this. How many ways are there to do that? So I will leave this as a challenge. I am also one of the managing editors of the Fibonacci Quarterly, which works in close association, of course, with the Fibonacci Association. And so I am happy to make this a problem that we will submit to the problem section of the Fibonacci Quarterly. So if you guys work on this, you will have a submission. And you'll have something you can put on your resume. Is there a nice answer? Is there a nice sequence of the number of ways you can do this? Can you come up with a nice recurrence, or is the recurrence going to become much harder? All right, so this is a good place to stop. I will send an email to people just to get a little bit of a sense of how things are going. Is this the right speed? Is this the right level of material that you're finding interesting? And then just adjust things a little bit accordingly. But induction is a nice thing where there's a lot we can do. Okay.